Welcome to our LB2A demonstration source video. This video is intended for representatives. It shows how to use the LB2A source to demonstrate the functions and features of LadyBug Power Sensors. Customers may also receive benefit from this video. In this video, I'll be using the LB2A source, an LB480A power sensor, an LB5918A power sensor, two USB cables, a 10 dB attenuator, a 30 dB attenuator, and SMB to SMA triggering cable. The LB5918A sensor that I'm using for this demonstration happens to have option SPI, which is an optional cable that allows connection directly to a microcontroller without the use of USB. If you'd like to make the noise measurements that I demonstrate at the end of this video, you'll need the SMB triggering cable and the attenuators. The demonstration source has a trigger output connector, an RF output. It has a amplitude or power level switch, high and low, and it has a modulation on or off switch plus the USB connector. When you're making average power measurements, such as with a true RMS sensor, you can actually use the modulation on-off switch for power level, since the true RMS sensor will average the pulse, and that's also a good demonstration for the customer. For this first demonstration, we won't need any attenuators. We'll simply connect the LB2A source to the LB5918A sensor. We're using the 5918A and PMA12 precision power meter. I've started it up, and I've set my source to pulse off, and you can see the upper level is a little over 5 dBm and the lower level is minus 24 dBm. Now I'm going to open a strip chart, and you can see the sensor, the measurements from the sensor. Each dot represents one measurement coming in. Now I can turn the power level down and back up, and you can see the measurement change. And you'll notice that the averaging is set at 10 averages. That's the default when the customer starts the sensor. So here we'll change it to 100, and that'll slow the measurement down. It'll stabilize it. So if this were a low power level measurement, you'd get a much cleaner measurement, and you can kind of see the settling time here as the power goes up and then back down again. Now I'm going to go ahead and set it to 500. Now 500 averages is pretty close to 20 seconds, so it's going to take a fairly long time for the measurement to come to stability. Since it's a dBm scale, you'll see the low power levels make a rapid change. However, when it comes time to the actual stabilization, it will take quite some time for that to occur. So we'll put that back to 10. I'd like to point out here that different manufacturers and even different model numbers have a different time per average. In this case, the LB5918 and PMA12, an average is about 20 milliseconds by default. You can change that in this particular sensor. You can set what we call MRAT, or measurement rate, and adjust the time per average. And our other sensors, like the LB478 through LB680, one average is about 500 microseconds. So to get the same level of stabilization in those two sensors, you'll have to use a completely different amount of averaging. It's not possible to show you all the sensors, features, and capabilities in this short video. The purpose of this video is to show you how you can use the LB2A demonstration source to generate the signals required to show some of the capabilities of our power sensors. So I think we'll close out this basic demonstration and move on to some more advanced measurements. Now we'll take a look at the power meter panel, which works with a 478 all the way through the 680 power sensors and delivers average power plus statistical pulse measurements. Now let's take a look at the demonstration source and an LB480A sensor set for average power only. In fact, any LB 559, 579, 589, 478, 479, 480, 679, or 680 will make this measurement within its range. We have averaging available, and it's just an average power measurement. The sensor can make the measurement very, very rapidly. I'll set my averages down, have it at 500 here. The default for the sensor is 75, and now we have 75 averages, and you can see the power changes virtually instantly. It's a very, very rapid measurement on the 480. And that's about all you can show folks with the power meter panel. Now let me turn on the pulse panel. Now that's this button in the upper left, and using the demonstration source, which will put out a stream of pulses, you can engage the pulse measurement capabilities of the sensor. Now this is a statistical pulse measurement. Now the 480 will also make a triggered measurement in the pulse profiling panel, which I'll show you in a few minutes here, but this is the statistical pulse measurement, which you can make with a 478, 479, 480, 679, and 680. When I click this button, you'll see on the right here will open the pulse panel. But now let me turn on the pulse, and you'll see what a nice measurement you get with this sensor and with the demonstration source. You can show this to your customer, and now the duty cycle of the pulse that we're presenting is 11%, and the crest factors here. Now this is our pulse power. It's moved when we switch to pulse power. And our peak power is here. They're almost the same, meaning there's no overshoot. If we had a pulse with a lot of overshoot, then this would be higher than our pulse power, because the overshoot would be picked up as the peak power. And here's our average power down here, minus 33. And you can remember that number because that's the average power of this particular signal. I can turn the power level up and down. Now we use the same setup with the LB480A and the LB2A demonstration source with no attenuators, and we'll start the pulse profiling application and make a few measurements there. Okay, now I have the pulse profiling application open, and I've got a 480A sensor connected to the demonstration source. I've got it in continuous wave, and I've got the power set to high. So the line here represents the actual power level. And now I'm going to turn the pulses on, and this makes a nice display to show customers. And here you can zoom in on the pulse by just clicking and dragging, and now you've got this detail. So the demonstration source is really nice to use to show customers things. This particular measurement is different than the statistical measurements, even though we see a lot of the same measurements over here. This pulse profiling application actually triggers on the pulse and measures the parameters of the pulse, while the statistical pulse measurement calculates the measurement statistically. It does not need to trigger on them. All it needs is a bunch of pulses to grab the data on and calculate it. So here you can show the customer his pulse stream in a kind of a nice way. I can turn down the pulse here, and now if we want to make an automatic measurement, let it calculate the pulse parameters for us, we just click auto measure and start measurement. Now you're going to get this warning. I did this just so that I could show you, because this is a common error that we get, and this is because the statistical triggered system requires at least 2 complete pulses, and while it looks like we have 2 complete pulses, it just needs a little bit more. So we're going to have to increase the sweep time, which is the time that the trace takes to cross the screen. And right now it's 200 microseconds, and we're going to change that to 500. We'll get a bunch of pulses, and now we can make an automatic measurement here, and you'll see there's our 33.7 average power, dBm average power, and our crest factor, duty cycle, which we all were able to get on the statistical measurement, but we weren't able to get the rise and fall time, and here we're able to actually see the rise and fall time. We're able to actually measure the pulse repetition frequency, and it calculates the time and frequency for us, and the pulse width, which we're not able to get with a statistical measurement, which does not give you any time functions. Now we can still zoom in and see a lot of detail on our pulses. So you can see that the demonstration source is very handy to show customers exactly what the sensor does. There's all kinds of other features that the power meter has, and you might want to become familiar with those so you can show the customer the different features. But this is really about general use of the demonstration source. Next, I'm going to show you one of my favorite things to do with the pulse profiling meter that is really nice to see about noise reduction. Now, this is a kind of an advanced measurement, but it really does show you what a nice sensor this is. I've added the triggering cable, and I've added 40 dB of attenuation between the LB2A source and the LB480A sensor, and we're going to be making a pulse profiling measurement. So this is a triggered measurement, and the reason I have the triggering cable installed is because part of the measurement is going to be made with the signal in the noise floor, so you'll hardly even see the signal, and the noise will be higher than the signal, so the sensor won't be able to internally trigger on the signal. So we're going to use the external triggering input from our signal source. Okay, now this is a nice demonstration. You can show the low-level measuring capabilities of the LB480 pulse profiling sensor. I have the demonstration source connected. I have the modulation turned off, which I turned it off just this very minute. So now it's a CW signal. It's attenuated down to the noise floor. I've got the same 40 dB of attenuation on the sensor. Now I'm going to turn on the pulse, and you'll see that it just comes in as a bunch of noise. There are two reasons for that. One is there's insufficient signal because the noise is actually at a higher level than the signal is. The sensor cannot identify the point to trigger. So I have connected the external triggering cable, which you saw in the picture, and now we're going to go into triggering and display, trigger source, and I'm going to set that to external TTL. So now it's triggering on the external signal from the little source, and the source has a delay placed before the pulse occurs after the trigger. So right here you'll see that in fact I can zoom in on that and show you a little bit better the delay that occurs before the pulse. This is the pulse right here in all this noise, and I'm going to put that back to 500 so we have multiple pulses on the screen, and we can make some measurements with this. So now that's not a very usable piece of information with all that the noise being as high of a power level as the pulse is. But we can average that out, and I'm going to do that by going into averaging, and I'm going to turn on 50 averages. Now this is 50 traces, so there's a lot of averaging going on. It's going to take the whole trace and it's going to stack those traces on top of each other and do a significant amount of averaging for us. So it's going to take it a little bit of time. I'm going to set to manually reset, so it's going to start averaging, and you'll see our pulse come out of the noise. There's our pulse, and we can actually get a good measurement on the pulse over here. The duty cycle is 11. It's just like it was before. You can see that, and so there's a nice clean pulse. If I wanted to, I can change the scaling on here and enlarge this so that you can measure it more accurately. I could place a marker on it here. I'll turn on a normal marker, place it right here in the pulse top. So there's the power right there at the top of that pulse, 63. We're actually below the sensor specified measurement range. So this is what you get when you buy a quality power sensor, where actually our off-state power is close to -70, our on-state power is -63, outside of the sensor's measurement range. Now I'm going to do one more thing that'll allow you to clean this signal up even more. So this is a fairly narrow pulse. It's not a real wide pulse. but we have a 10 megahertz filter applied on the front end. Now when you apply a filter to the front end of a power sensor, it's a video filter, so the signal is detected, and inside that detection there's all kinds of noise. That noise covers a broad frequency range, and with the 10 megahertz filter we're letting in a lot of noise. And we can block out some of that noise and still maintain the accuracy of our pulse. So I'm going to start by placing a 3 megahertz video filter on this. And that should filter out some of our noise, and you'll see the pulse is even getting better. We are starting to see a little bit of rounding, and that's because at 3 megahertz we are distorting our pulse just a little bit. So we can go up to 5. And you can show the customer with this demonstration source these features that really allow you to drill in on a pulse nicely. I'm going to turn up the pulse power just to show you what happens with all the averaging. The reason the pulse is slowly coming up is because of the 50 averages that we have set. I can set that average back down a little bit, and I have a high power pulse. It'll still stand out. In fact, I'll just turn off the averaging, and you can see the noise come back in. But now our pulse power is high, so we're actually coming out of the noise, and in fact you can see the pulse power is now minus 33 dBm. I've placed the LB2AVideo1 true RMS sensor back on the source, and I've left the attenuators in place. So we're going to make some low-level true RMS measurements. So these are very useful for some customers, but you don't get the pulse profile, but you will get a very low power level. And once again, we'll be looking at power below the sensor's calibrated measurement range. Okay, now we're going to use the demonstration source on a CW signal just to demonstrate how we can pick the signal out of the noise with a good quality power sensor. So the source is outputting about 23.5 dBm, and I've placed 40 dB of attenuation on the sensor, so that puts me below the sensor's measurement range, and we're showing that on the screen right now. And I'm going to now turn the power up to high, and you'll see it move up to minus 33, which is what we would expect. And now back down again. And now I'm going to turn on a strip chart so that we can actually see what's going on here. Now you see there's a lot of noise in the signal. And I'm going to run the power again up and down. So the line here is the minus 60 dB level that the sensor is capable of measuring. I'm going to actually disconnect the source so it's actually unplugged, and you might see a power level change there, but it's kind of lost in the noise. So I'm going to turn it back on here, and so now we have our source on again. I'm going to go back to the averages and just show you what you can do with 250 averages. 250 averages is on the order of about 10 seconds of averaging on this sensor, and it will smooth out the line a little bit, and you can see that we are seeing a power level, you know, minus 62. Well, it shows 62 up here, but minus 62 or so. And you might be wondering, is that actually the signal? Well, I'm now going to unplug the power sensor, and you'll see that in fact it is a signal. You notice the slow change. Remember I mentioned that the averaging is about 20 seconds, but you can clearly see that we've now dropped down in power, and so even though we're making an essentially an uncalibrated measurement, plugged it back in now, the sensor is actually pulling the signal out of the noise, and if we were up into the 60s we would be getting a good measurement on this sensor. So that's another thing you can do with the demonstration source on a true RMS sensor, just to show a customer what a good sensor will do around the noise floor. Thank you for watching our LB2A demonstration video. In this video, I've shown some fairly complicated measurements that take some time to set up and display. You may not have the opportunity to do this at most customers, but if you do these yourself, you'll be very familiar with the sensor and with the kind of measurements it can make, and you can show a customer a basic measurement in a very short time, and then if they ask the questions, you can go into the detail and show them pulse measurements or low-level measurements or whatever kind of measurements the customer may want to see.